Introduction. I hope you can, maybe just one feedback. Do you hear me clearly? It's fine.
We can hear. So the participants, if you can hear, please say yes in the chat, maybe.
I guess
okay.
If you can hear me, the others can as well. Oh yeah, I hear some chat messages. I see some. Great. Well, I'm very honored to be invited to this very interesting webinar series of you guys, Karen and others. And today I want to talk a bit about this kind of idea of the thermodynamics of electrochemical interfaces that or that I and of course also others developed in recent years. And so I have a kind of a more abstract ground canonical view of the such electrochemical interfaces and how we can simulate them. And in particular, I want to talk a bit about some maybe new detailed properties that we have looked in recently, which are in particular some kind of pH and potential effects that you can access now with kind of fully ground canonical simulations of electrochemical interfaces, and in particular when you use implicit solvation models. So this is already kind of the overview of my talk. I will mainly, this will be a kind of nearly purely, I would say, theoretical talk. I will mainly try to describe our idea of how these electrochemical interfaces can be described in terms of the thermodynamics within a kind of fully ground canonical description. And I try to kind of describe how this relates to the very early or the original computational hydrogen electrode approximation. So there are some kind of small, maybe I think conceptual differences, but they also, of course, very close relations. And I will try to kind of make these or develop these ideas in this talk. And then at times I will also compare between theoretical results and some experimental results. And so the method that we use, or that I use, is, as was already said, density functional theory calculations in combination with an implicit solvation model. And the rest is kind of only concepts borrowed from, let's say, the ab initio thermodynamics approach or approaches. The main concepts are essentially described in this paper that we did together with Oliviera Andreusi and Nicolas Mazzari. And so to kind of set the stage for this kind of thermodynamic description, I think it makes sense to look first at the basic properties of electrochemical interfaces or electrified interfaces. What are kind of the relevant parts of this interface? And I think it is very insightful just to have this, or keep in mind this kind of one basic definition of electrochemistry. This is a definition given kind of by Schmickler in his book Interfacial Electrochemistry. And here he says, electrochemistry deals with the processes at the interface between an electron conductor and an ion conductor. And that kind of nearly tells us everything I think we need to know how we should address these calculations and what are kind of potential or relevant degrees of freedom at such interfaces. And so I made this kind of very approximate sketch how I view or how one can view the electrochemical interface or an electrified interface. You have on the one side, of course, the electrode, and then here an interface between this electrode, mostly a solid, and some electrolyte solution. And the most kind of, I think, let's say, relevant parts of this interface are, in some sense, the electronic surface charges, then anything that happens here in this inner double layer where you could have adsorption or electrosorption of ions or some molecules. And you have then here a bit farther apart away from this very interface, you have potentially a diffuse double layer. So still a kind of region of space where the structure of the solvent or composition of the solvent is different from the composition and structure of the solvent in the bulk liquid. Now, so having kind of put this forward, then let's look how we typically address such system in calculations. So the kind of one, I think, defining property of electrochemical, or one, let's say, clear property of electrochemical interfaces and reactions at such interfaces is that we might have electron transfer processes, and in particular also changes of chemical bonding at this interface. And for this reason, you typically, I think one needs a kind of method that can describe somehow electrons or kind of chemical bonding appropriately. And the kind of straightforward method for this is to use some ab initio methods. Now the problem is kind of the size of this interface. And in particular, one problem is that this diffuse double layer or the size of this diffuse double layer depends, of course, strongly on the composition of the electrolyte, and typically can be of the size of certain nanometers. And so it's kind of very problematic to describe this diffuse double layer realistically with ab initio methods. And so in let's say, I think the most part of the theoretical works, what the community has agreed on is that maybe we kind of, let's say, ignore for a moment, at least in the past, we ignore for a moment these kind of diffuse double layers story, and we focus especially on all the chemical bonding and things that happen at this inner double layer. And this kind of approach is, or I relate with this approach, the so-called computational hydrogen electrode approach, where we have agreed that that we can kind of estimate the, let's say, thermodynamics of this interface by just simulating this very inner double layer. Now the problem, or not the problem, but the kind of limitations we have here is that because typical, then for example, DFT codes are use periodic boundary conditions, we have kind of a problem to treat systems that are not charge neutral. And so because of these limitations in periodic boundary conditions, typically what we do is we treat or we kind of impose a priori on our system that we treat this inner double layer charge neutral. And with charge neutral, I mean that we do not, for example, look at any possible variation of the electronic surface charges. And this is kind of simply related to the fact that it's problematic to be addressed in DFT or in periodic DFT codes. So in some sense, therefore, addressing or looking at these electronic surface charges is kind of closely connected to the diffuse double layer. And so because it kind of this problem of charging the surface can in principle only be lifted by having some appropriate countercharge model. And the calculations that I will talk about today will be in particular calculations where we have such an implicit continuum solvation model in our simulations that allow charging of this double layer, or kind of introducing excess electrolyte charges here, which then in effect also allow basically to address or to change the number of electronic surface charges. And so this is kind of the definition or my kind of definition between the different these two different approaches I want to talk about. The CHE approach, where we only look at kind of these charge neutral inner double layer structures, and a kind of fully ground canonical approach where you also include some double layer degrees of freedom, and thus can also now address this electronic surface charge degree of freedom. And as I've already said, explicitly treating this diffuse double layer is always, well, let's say at least difficult. So the way we do this, or I do this, is using some implicit solvation model that that allows also to address the electrolyte and electrolyte excess charges. Now, how do these implicit solvation models typically look like? Well, the idea is that the solvent in, or this electrolyte solution in average, if you take an ensemble average, it is kind of relatively unstructured typically as soon as you're a few angstroms inside the solvent. And so there's the clear idea that potentially you can describe this solvent and all kind of solvent-free energy changes by a continuum representation of this solvent. And this continuum representation would essentially have two ingredients that would be just a dielectric medium with an effective dielectric constant as I've just kind of drawn here, and a certain type of electrolyte model that might be just kind of Helmholtz planar countercharges, or even some kind of more refined Poisson-Boltzmann or modified Poisson-Boltzmann descriptions of this electrolyte. And that's in very kind of direct agreement or identical to how electrolyte solutions have been described classically, like let's say 100 years ago already. And so how do these then implicit solvent models couple to our DFT calculation? And this is a bit sketched out here. Typically, we have then a quantum mechanical cavity, and this cavity, then what you define is kind of an interface between this cavity and our continuum model. Beyond this interface, we describe, let's say, the energetics or the effective free energy changes of the solvent with such a continuum model that, as I said, consists of basically a dielectric medium and the electrolyte model. Now, such explicit or quantum mechanical models coupled to continuum solvation models, that has been out there already since kind of a long time, especially for molecular quantum chemistry codes. But it has only been really implemented, at least in a wide variety of codes recently, that in codes that can treat solids, and in particular also systems with periodic boundary conditions. And so the model I'm using here, or we are using, and that is kind of also kind of common in many other DFT codes, or in many DFT codes, is the so-called self-consistent continuum solvation model, where this boundary here is chosen self-consistently based on some electronic charge density thresholds in this system, also of this explicit system. So here are just kind of some reference papers. So there are also, of course, also many other people who have contributed to, let's say, improving such or implementing such implicit solvation models. I'm just kind of citing those that use especially the self-consistent continuum solvation model approach, like Andriussi and Mazzari, and then also Stefan Ringe, that you all know at DTU, at least I think, and Oberhoff and Reuter. So what I've been working then on in my time with Nicolas Mazzari was mainly to look a bit better at the properties of these implicit models and how accurate they are in describing certain properties of the electrochemical interface. And in particular, what we found is that in particular, this parametrization, or the parameters that define this boundary, are very important for the overall, let's say, accuracy of this method. In particular, changing those, let's say, charge density thresholds that define this boundary influence strongly potential of zero charge and capacitances. And also it turns out that of course, not all properties of the solvent can be described with such a continuum model. And it turned out, and we looked here at basically, or we compared here results from purely implicit solvation representations. We compared them with purely explicit calculations. And what we saw is that in essence that you need kind of a few number of water molecules at the surface treated all explicitly to get really like rather or very accurate results in the computations. I will talk about this in more detail at a later stage in this talk. So having now a bit outlined this implicit solvation models, I want to first kind of address the question, is it all relevant? Does it really, do we have to make all this trouble of describing these kind of far apart solvent degrees of freedom? Is it really relevant for observables in electrochemistry? And so I want to give a first very maybe simple example, but at least you can see that, of course, there are many observables that kind of depend also on the description of this electrolyte and of the double layer very strongly depend on this. So this example is kind of a very simple system. This would be a silver 111, just a silver 111 electrode in solution, potentially with ions dissolved in the electrolyte solution. And you see here the experiment on the left side. What you do is here, you put the electrode in solution, you apply a potential, and you measure the electronic charge density on the surface, or the surface charge in essence. And what you see is in the pure solution, by application of a potential, you of course add additional electrons onto the surface just purely by double layer charging or capacitive charging of the double layer. Now, if you add ions in solution at a certain potential, you can then electrosorb these ions, and due to these adsorbed ions, you can add additional electrons onto the surface, or rather remove them from the surface, and that's why you can see this jump or this stronger increase in the electronic surface charges. Now, how do our kind of, or a simple how does a simple calculation of this kind of experiment look like in these two approximations, computational hydrogen electrode and these fully ground canonical calculations? And as you can imagine, the CHE model that assumes the very interface, this inner double layer non-charged, is kind of not able to describe this capacitive charging. And so naturally in the simulations, if you look at the surface charge, which you don't kind of change by definition, you could not see any surface charging, or you would not simulate or see any surface charging when applying such a potential, for example, for the clean surface. If you add some ions in solution, of course, you also get the electrosorption, and so you get this increase due to adsorbed ions. But you can already see that kind of this, even this simple experiment, you have some kind of trouble to reproduce this in the simulation. While in the fully ground canonical approach, where you allow for capacitive charging, you can of course get this, this kind of baseline slope for the clean surface when you apply a potential. And you can also see that also the electrosorption of these ions is described kind of more similar to what we see in experiment. So this is kind of a very kind of maybe drastic example, and you might say, okay, this is maybe trivial, you know, you just add this baseline slope to your simulation because you know you don't have it. But so the question is rather, are there also other observables that are kind of not described intrinsically in this original computational hydrogen electrode approach? And it turns out there are. And I've just listed a few of them, and I will later talk about some of them in detail. So we've said already surface charges variable in fully ground canonical calculations and experiment, and fixed in some sense, a priori fixed in the computational hydrogen electrode model. And this kind of, let's say, this directly translates, in fact, then to a different behavior when you look at the interface, at the interface energy as a function of the potential. So in experiment and these fully ground canonical calculations, your interface energy can be or is typically nonlinear in phi, or in phi, where it is always linear in the computational hydrogen electrode approach. And you see here, very simple system. This is an experiment here on the left from 1926 by Fromkin. This is just a mercury electrode in aqueous solution, and you can see that the interface energy here as a function of the potential is clearly curved, and it's kind of nearly looking like a parabola. If you would do if you would simulate the system within the computational hydrogen electrode approach, you would get interface energies that don't depend on the potential. They are just these horizontal lines. And in general, they are, as I said, linear, whereas in general, linear in the CHE approach, while being nonlinear normally in experiment. As an effect, you also see a different behavior, in fact, when you look at surface Pourbet diagrams. So in the experiment in fully ground canonical calculations, by definition, kind of, the Pourbet diagrams are at least two-dimensional. So you have at least these two degrees of freedom, the pH, for example, and the applied electrode potential. And you see this diagram, which is taken out from this publication here. It's in effect only in the supporting information, but nevertheless, you can see this this plot is fully two-dimensional in some sense, while if you would do this kind of analysis within the CHE approach, you could only find horizontal lines. In particular, these different surface phases would not depend on the pH. And so in some sense, this Pourbet diagram is only one-dimensional effectively, and this one dimension upon which in which the phase diagram changes would be, for example, the potential on the RHE scale. Now, the relation, I mean, this kind of can be explained quite kind of naturally by different description of the adsorption energy. The adsorption energy in general could be pH dependent, but is typically not pH dependent in the CHE approach. And it can also be directly related then to, or can be easily related, these differences to differences in the description of the electrosorption valency. This one would be possibly non-integer in experiment, while it would be kind of fixed to an integer value in the CHE approach. So in order to now a bit better understand where exactly then a kind of these where exactly the problems lie, let's say maybe, I want to kind of derive here a bit this fully ground canonical approach and exactly explain what we are doing here. And so I started the kind of basic definition, or I'm looking first at the basic properties of this electrochemical interface. We have to look first for the relevant degrees of freedom. And as I've said already, there's for sure, or I would say it's kind of pretty obvious, we have at least 2 degrees of freedom, just based on the definition, which is the number of electrons, or some kind of the electrons, let's say, and the other degree of freedom, that's the number of ions, or the ions in the electrolyte solution. Then the next question, what are the relevant thermodynamic variables that we can tune in the experiment? And this is also kind of straightforward. If we just look at a Pourbet diagram, these are typically two-dimensional, and we have on the one hand the pH, and on the other hand the electrode potential. And so this tells us that the relevant thermodynamic variables are the electrochemical potential of the electrons, so the electrode potential, and the pH, which relates, of course, to the electrochemical potential of the protons, or of any other adsorbats that we might want to look at. And so taking these things, these two things together, it's kind of clear that we want to describe this interface in a ground canonical ensemble. So we are kind of looking for a ground potential that depends only on these electrochemical potentials of the species in our system. Now the question is, of course, well, can we address this directly in like standard calculations? These ground potentials as a function of electrochemical potentials, and well, I think we're all aware this is typically a bit harder to address in terms of how this. I mean, you would have to think about ground canonical sampling, for example, particle insertion moves, etc. So this is typically not what is done, because any DFT code would traditionally be limited to do simulations, or you would always do simulations at fixed particle number. And that means fixed particle number of your atoms, but it also means that typically at fixed number of electrons in your system. So this is what we want, the ground potential, but what we typically can simulate is rather like a Gibbs free energy. So as an energy at fixed extensive variables. So just here, my naming convention alpha would be just kind of a certain interface configuration, and these n's are just describe the composition of our interfacial system. And in particular, we will also treat the electrons as an independent degree of freedom in this fully ground canonical approach. Now, how do we get from here right to the left to the ground potential? Where we do just a kind of Legendre transform, and this Legendre transform in a most abstract sense consists just of 2 steps. The first steps is we would have to define these Gibbs excess energies. These Gibbs excess energies are describe kind of the energy cost constructing this interfacial system from its constituents, and these constituents derive from some thermodynamic baths or reservoirs, and these reservoirs are characterized by the electrochemical potentials. And so these Gibbs excess energies are just, let's say, the Gibbs free energy of this interfacial system minus then the energies for taking the constituents from these external baths. And having now constructed these or written down these Gibbs excess energies for many different configurations, alpha and compositions n, we can then derive the ground canonical free energy as the most stable of those sampled Gibbs free excess energies. And so, yeah, the only thing you want to do is here being kind of accurate in your sampling, and then so you can approximate or get a very accurate, let's say, estimate for this minimum in the excess energies, which would be then your estimate for the ground potential. I have not yet clarified maybe what are kind of maybe important points here that are not totally clear, maybe on an abstract sense. So what is actually these electrochemical potentials? What is this number of electrons that I call absolute number of electrons here? And what is like this electrode potential? So what is kind of important here is, in essence, that you we treat this all these energies on a consistent, of course, energy scale, and that means also then for electrochemical interfaces on a consistent electrostatic potential scale. Because basically we have here electrochemical potentials of charged species. Their value depends on the electrostatic reference scale, and for this reason we need to kind of be a bit kind of careful how to choose these values and how to reference all those values correctly. So it turns out when we use these refitted or some let's say specific SCCS parameters that we refitted in particular for platinum in this work here, what we see is that kind of this energy is then consistent with the absolute, with an electrostatic reference that corresponds to the absolute potential scale in the electrochemical sense. So basically the electrostatic potential of the vacuum above the solution. And so we've now clarified, okay, we should, at least within this kind of let's say parameters of our implicit model, we should express now the electrochemical potentials for electrons and ions on an absolute scale. I'll get into this in a minute. The other question was this absolute number of electrons. What is kind of this? So this is basically, or you can easily see or derive what this should be. This should, in essence, only, or this is directly given by being just consistent in this description, namely that the total number of electrons in your interfacial system should correspond to the sum of all the electrons that are taken into account in these thermodynamic baths. And so you come up with this description that, or with this formula, that the absolute number of electrons should be the number of kind of electrons that are there to compensate for the ionic charges, plus some additional net surface charges that kind of build up your diffuse double layer, or that are screened identically in the diffuse double layer. Okay. Then also still maybe not totally clear what is these Gibbs free energies. Is it easy to calculate? Well, in all what we did so far, we also use this typical approach or approximation that we say we can approximate this free energy difference here as the difference between DFT total energies plus some correction due to adsorbed vibrations. And then lastly, how to express the electrochemical potential on the absolute scale, for example, of a proton. And here we also rely just on these kind of this approach, the standard approach. We use DFT values plus experimental values. So you can derive then the electrochemical potential of the proton on the absolute scale from this equilibrium at SHE conditions. And so you can relate the electrochemical potential of the proton to the hydrogen gas chemical potential. And so here we are kind of done. This is the whole kind of method for this fully ground canonical calculations. And so we could stop here, but I think it makes sense now to a bit summarize and put it in perspective of the typical computational hydrogen electrode approach, because it looks very similar, as you can agree, I'm sure. So what is the exact difference, or what is exactly what we do a bit differently here? And so in essence, the only thing that we do differently here is that we allow for these electronic excess net surface charges. And so you can directly see, actually, if you remove this net surface charges that are relevant for the capacitive charging of the double layer, if you remove them, then all these equations fall back or become the identical equations that we use, or that one typically uses in the CHE approximation. But what you can what you can learn from this insight is that ultimately, when we do the computational hydrogen electrode approximation, that what we effectively do is we leave away this net surface charge degree of freedom, and therefore we miss kind of 1 degree of freedom in this minimization process, and therefore the computational hydrogen electrode energetics can only be an upper boundary estimate for the interface free energy, for example, or for any energetics. So to make it a bit more clear, while or at least in my eyes, while one would at least want a 2-dimensional kind of configuration or phase space in electrochemical interfaces, while one wants to sample, in fact, this 2-dimensional phase space, which is related to number of adsorbats and number of electrons on this surface, this is exactly what we do in the fully ground canonical simulations. We do not do exactly this in the computational hydrogen electrode approach, but we kind of leave away this, this degree of freedom of the net surface charges, and thus this 2-dimensional kind of phase space is reduced to a 1-dimensional phase space, and that is then directly related to also what I said before, that the Courbet diagrams are not 2-dimensional in the CHE, but they are rather 1-dimensional, or they can only yield 1-dimensional plots in the CHE approximation. So just a kind of short demonstration that this kind of abstract result or insight that the CHE approximation is really can only be an upper boundary estimate for the interface energy. This is a calculation for gold surfaces in solution, just pristine gold, no adsorbats. And we have looked here at gold 100 and the reconstructed gold 100 surface. And you can see first in the CHE approach, we get potential independent interface energies, while in contrast, the fully ground canonical calculations, they have a potential dependence. They have these kind of parabolic shapes. We can see these results are always exactly below the CHE line, which relates to the fact that CHE can only be an upper boundary estimate for the interface energy. And what we can also see here is that in these fully ground canonical calculations, we can in fact, at least kind of from the trend, we can, for example, explain the lifting of a surface reconstruction. In particular, normally the gold 100 surface is reconstructed as a quasi-hexagonal reconstruction, for example, in vacuum. But in solution, when you apply positive potentials, you can lift this reconstruction. And this is exactly what we see in these simulations, that the blue reconstructed surface energy or interface energy is becoming less stable than the unreconstructed surface at positive potentials. So that's kind of a, I think a first kind of interesting insight maybe. But more recently, we try to get a bit even more insights on a more abstract level. What is it actually that is significantly then different in these fully ground canonical calculations, and can we maybe make some predictions when they are really relevant, or when do we expect relevant differences between this kind of CHE calculations and the fully ground canonical calculations. And for this, we looked in essence at a second order Taylor expansion of the DFT energy of our interface energy as a function of the electronic surface charges. And in all fairness, I want to say these ideas are kind of really like basically identical to what has been also looked at or published already in Karen Chan's group, like by Gauthier. There are a few works by Gauthier now recently that discuss in some sense exactly the same thing. I'm just kind of maybe using here a bit different words, but the essence is really the same. So what happens is, if you look at the second order Taylor expansion of the interface energy as a function of the surface charges, you can then analytically derive the surface excess energy. So the charge equilibrated excess energy, meaning the interface energy at applied potential. And what you see is that there's a first term, and this first term corresponds then to the kind of linear term in the applied potential. And what it turns out is that this first term is exactly identical to the energy as it is described within the computational hydrogen electrode approach. And then you have kind of then higher order terms, and the first kind of non-vanishing here higher order term is quadratic in the potential, and it corresponds identically to a kind of, or to the charging or the energy contribution due to the charging of a plate capacitor. And this is kind of double layer charging under the assumption that your interfacial capacitance is potentially independent. But this kind of analysis, what this analysis allows you to understand is that the CHE is very easily relatable with the fully ground canonical results. In particular, it is exactly a first order approximation to the kind of fully ground canonical charge equilibrated excess energy of an interface. One can then go further, and again, this is also, I think, identically done in some sense by Gauthier et al. We can also look at the relative stability of different surface configurations, alpha and beta, and you can kind of find then that this relative stability of two different surface terminations or compositions, alpha beta, is exactly the energy difference as you derive it from the kind of, or as you would compute it from the computational hydrogen electrode approach. But then you have some additional contributions in the second order model. And the first contribution looks like this. It is linear in the potential and proportional to the work function difference between those two configurations, alpha beta, that you look at. And the work function difference here is also kind of then easily relatable to Azobert dipoles in some way. And it turns out that these energy contributions here are kind of really identical to what has been kind of published in the classical electrochemistry literature since many, many years. Like the earliest I could find was here in 1926 by Fromkin. And yeah, there's a second contribution that is in principle could be in principle important. That is a contribution due to the capacitance difference of these two states, alpha beta, for example, due to altered interfacial water properties for these two different systems, alpha beta. One important point here that I want to make is that it turns out with these kind of formalism, and the formulas look maybe a bit kind of complicated, but we think kind of some complication just is there if you want to be accurate. What it turns out that you can do then some kind of analytic limit, for example, for single adsorbents on the surface, and you will see that this analytic limit for infinite cell size, so where you try to understand like how can we describe single adsorbents on an infinite surface, what you can see then is that these fully ground canonical results are still also in this limit different than the CHE results, which I just want to put here because sometimes I feel like there's the idea that in the infinite cell size limit, such kind of work function differences or so go to 0, and there's no difference. But if you do the limit, like with these formulas, there's really still a difference present also in this limit. Just maybe to mention these kind of ideas or these things I've just shown, or I'm going to show now in the next few 5 minutes. This is all then summarized in a publication that we've just submitted, or that I've been working on since some time, but we just submitted it. Yes. So what does this? What insights can we gain from the second order approximation? So in fact, we can also now understand where potential pH shifts can derive from. And here we looked, for example, at protons on platinum-111. And what we found is that in these fully ground canonical calculations, this proton electrosorption peak position shifts with pH. It shifts to lower potentials on the RAG scale with increasing pH values. And this is in very good agreement with the experiment. And we could also kind of see that this kind of the order of magnitude, or the let's say the size of this shift, is directly related to the Azerbaid-induced work function changes. In addition to this, we can also analyze this other property that I've mentioned already before, that is the electrosorption valency. So the property or this electrosorption valency that describes in essence the number of electrons that flow onto the electrode upon an electrosorption event. And then you can, in the second order model, analytically derive how the electrosorption valency, what its value should be. And it turns out that you can separate it into two contributions. Let's say you have first kind of the CHE value, and the second contribution kind of double layer related value. And this double layer related value is again proportional here to the work function change per Azerbaid. So again, related to Azerbaid dipoles. We have tried to do these predictions in these simulations kind of go roughly at least in direction of what is measured in the experiment, and it turns out that our agreement is quite good, I would say. So this is now a comparison to for the electrosorption valency for halogens on silver 111, and we looked here at this series chlorine, bromine, and iodine, and what we can see is here in the orange star, that's the experimental value. So you can clearly see here experimental values that are different from -1. So this electrosorption valency for chlorine is somewhere here at -0.5, and for iodine somewhere down at -0.8. And in the experiment, you cannot resolve this kind of dependence on coverage that we can resolve in our simulations. But what we clearly see is that in these fully ground canonical calculations, or let's say approximations to it, we can get the correct trends. So higher electrosorption valencies for chlorine, lower ones for iodine. And if you take the kind of coverage average, the average of these coverage dependent values, which is in essence the kind of average that you do in experiment, then you see also in average we are kind of close, rather really close to what has been measured in experiment. And clearly, what is clearly very different to what you obtain within the CHE approximation, where you always get an electrosorption valency of -1 in such simulations. And in particular, it turns out also this expression that I've just shown for the electrosorption valency is identically, again, identical to what others have already published in, I think, the 80s. Is kind of especially Schmickler talked in some papers about what can be expected, what electrosorption valencies can be expected, and how they are related to the Azerbaid work function change or the Azerbaid dipole. So now to going towards the end, I've maybe need still 3 minutes. This will be more like a summary or a bit like an outlook. It's kind of, I've just of course showcased a bit, let's say, representative simulations where we are kind of feeling, this looks quite good, or this is in quite good agreement with experiment. Of course, there are still many problems in terms of the accuracy of such simulation. simulations. In particular, I want to put forward here the interfacial capacitances are of course still a problem. So here we look at interfacial capacitances of silver 100 in dotted, dashed red experimental values, and you can see depending on your implicit solvent parameters, like for example green and orange, you can be quite off. However, if you kind of use some optimized parameters, red, you can kind of get roughly accurate interfacial capacitances. Here different properties we looked at, which is, as I mentioned already in the beginning, potentials of zero charge for metallic surfaces. Here again, we also see a bit some kind of inconsistencies, while platinum with this parameterization seems to reproduce in the theory quite well the potentials of zero charge in such implicit solvation models. So on the x-axis, you have the experimental value. On the y-axis, the theoretical one. We find that then going to a different material or different materials like gold, copper, and silver, you just have suddenly this shift. So there's some kind of inconsistency between for the potentials of zero charge when you go when you look at different metallic surfaces, and it's most likely related to interfacial charge transfer at these between water molecules and these metallic surfaces. So clearly we have a bit of a kind of, let's say, issues with capturing exactly these interfacial potential drops. And something I've also not totally had time to talk about is what is about the water vacuum interface that we had never have really in our calculations. And just to very briefly summarize here, one result. So we try to assess basically these two potential drops at the water vacuum interface and at the solid water interface, and we try to address this or analyze this by looking at the band alignment of semiconductors in solution, and in particular in fully implicit solution and in a fully explicit solution, and then in systems where we have just a few water molecules treated explicitly. And what we could see here is that in fact, if you substitute all the explicit water with an implicit model, you get kind of for the band alignment, and these are here down there, the different systems we looked at. So we get for the band gap alignment on the potential scale, we get clearly differences if we just substitute all the waters with an implicit model. However, if we just substitute, let's say, everything but the first water layers with an implicit model, we get kind of very consistent descriptions of this band alignment for these semiconducting systems. So clearly, the interfacial water effects and properties are very important, and clearly they can't be described fully in such implicit models. So this was this was kind of my talk. I want to, of course, thank all my previous collaborators and current collaborators. I want to thank the funding agencies, and I thank you for your attention. Here I'm just going to the summary slide, and I'm happy to have some interesting discussions with you now, maybe on this topic and on any topic related to electrochemistry. Thanks a lot. Yeah, I hear Stefan Ringe, but I guess somebody else will do the
yeah, so I think we'll, yeah, thanks a lot, Nico, for the great talk. I think so now we'll do the question answers. So I see that there's, let me just put the question in your chat window so you can also, can you see the questions?
Give me a second. Is this in the Q&A?
Yes, exactly.
I see open. There's no questions. Answers. What is the energetic difference? Sorry?
Yeah, go ahead.
Well, I see something answered one.
That's just, I'm sorry, I just put it there, but it's not answered yet. I'm sorry, but you can go ahead and read the question and answer it.
Okay, I'll read this question. The question is, what is the energetic difference between the infinite cell size limit and the approach that you mentioned? So, I I'm not 100% sure if I completely understand the question. I give two kind of answers. So because I'm not sure if it's related to the work by Gautier, where there's this kind of work called practical, I think practical considerations. I think something like this in the title, where there was described that you can have a problem in the, let's say, in the energetics for infinite cell size, like perpendicular to the slab. So how thick you choose your implicit solvent region. And that was especially a problem related to VASP-SOL. So here, I just want to say, if this is what the question was relates to, then this is not the question that or the topic I was talking about in my, or like that I mentioned in my talk. And I think this is a pure problem of the, let's say, energetics as or electrostatic referencing in the VASP-SOL, or at least at the time in the VASP-SOL kind of implementation. So there's no kind of problem with cell size if you use environ, in particular with all the periodic boundary corrections that are implemented there. Then the other if this is not this, this was kind of one potential answer, and the other answer, or if I interpret the question a different way, what I was trying to explain is, like, if you look at single adsorbats in a finite cell size, you have always kind of effects due to the kind of finite concentration that you're looking at, right? And potential, let's say, and you can clearly see that, of course, the work function change is dependent on cell size. And the point I just wanted to make is, you can kind of analytically derive the limit for the energetics for the infinite cell size limit. And it turns out the CHE result is not what the fully ground canonical result is. Now, I have a hard time now maybe to put it together in my head how the exact values look like, but ultimately, if I can go back in my talk, but ultimately the results look, the results look very similar to what I have written down in these equations. And as I said, it will be all kind of hopefully published soon in this paper, Electrosorption at Metal Surfaces from First Principles. Sorry for the delay. Yeah, so it looks all a bit like this. So ultimately what it will be is that this work function change between the two states becomes, in essence, the work function change per particle, which is kind of independent of cell size, and here we have the applied potential relative to the potential of zero charge of the non-covered surface in some sense. I mean, if you look at just single adsorbats on non-covered surfaces. So the math will be described in this paper, and I'm sorry, I mean, I can't really write it down now here, but I'm happy to kind of
Great.
talk later.
So Stefan, I've unmuted you, so you can ask your question.
Okay, can you hear me?
Absolutely.
Oh, perfect. Okay, thanks, Nico, for your presentation. It was really great to see, and I really like all these comparison with experiments and the good agreement that you get. So actually, I have two main questions. So my first question is regarding the constant potential method. So we always rely on using the absolute SHE reference potential. But actually the experimental value has a rather large uncertainty of like 0.2 or 0.3. And so my question is this not an argument for not using the constant potential? And should we rather use the theoretical absolute potential or the experimental value?
Yeah, I mean, that's a good question. I do agree kind of with you that this is a bit kind of always problematic to fit together, let's say, experimental results with a DFT calculation that anyways has problems to describe consistently, like work functions that would depend on the functional, for example, or can be strongly depend on the functional. So no, I mean, I agree with you. It's kind of an open question. I mean, I think in the formulas, if I and I'm sure you have also looked into this, in the formulas, if you write them down consistently, it turns out that essentially you kind of if you know that your work function is wrong in a bit in your simulation, for example, due to the functional, then you would also kind of have, I think, to have a consistent energetics, you would also kind of have to shift here, let's say, the experimental reference work function that you use then in your in expressing your proton electrochemical potential.
Yeah.
But because in that sense, then basically these terms cancel out, or they have to kind of, let's say, in some sense, these absolute alignments of the electrostatic reference level, they kind of have to, or they will cancel out then if you think of a reaction like in a CHE approach, if you think of a reaction where an electron plus a proton react with each other. So here they kind of cancel out, and that's why in the kind of CHE approach, you don't really, the problem is less kind of apparent, right? Because the absolute, there's no importance of getting work functions right or thinking about absolute potential and potential alignments.
Yeah, but could you not introduce such a reference then again, like by, for example, using the HER reaction and use that as the reference for your, because you said it will cancel out, right? Absolute potential.
Yeah, it will cancel out. If you do it consistently, it should cancel out kind of for one full reaction. Yeah. Okay. And I think, you need to kind of describe like these energetics on a consistent potential scale. And here you need to be a bit careful. That's true.
Mm-hmm. Okay, well, if I can I ask one more question? Or is there many other questions maybe?
You can go ahead. Just if it's short, please keep it.
Okay, yeah. So that's a short one. So actually for the halogen adsorption case, so you're calculating it at various coverages, and I was wondering just how you technically do it. Like, are you using large unit cells and varying your coverage, or?
Okay, no. So here, this is also kind of a bit fast, quick and dirty. Well, quick and dirty. I mean, so there is there was a lot of work done by Axel Gross's group on looking at halogens on surfaces. And ultimately what I did not look at different cell sizes because I didn't want to get into trouble with K-point sampling and inaccuracies due to kind of different cell sizes and K-point sampling. So ultimately, no, I did only fixed cell size with different coverages at fixed cell size. So, and it was kind of one could of course always try to be better. But it was, I can tell you, I looked at this in a square root 12 111 surface because there's some kind of experimental evidence of how the full covered surface looks like, at least for bromine and iodine. And they take, I think, a square root 3 structure. And so it fits kind of nicely then in the square root 12. And that's why,
that sounds great. Yeah, okay, then that answers my question. Thanks.
Thank you. Okay, so there's a question by Willem Offermans, and he asks, from a practical point of view, is the presented methodology implemented in some code, and how can one perform meaningful calculations?
So I didn't really talk about how to do or I tried a bit to describe how to do the calculations. So as I said, in principle, what you do, or I tried to say, but maybe didn't become totally clear. What you want to do is just simulate slabs with adsorbats at different coverages, of course, and different maybe structures, and you now in addition or beyond the CHE approximation, let's say what you also want to do is to change the number of electrons in your system. And so you can just do this in many codes. Now, all these codes that have an implicit solvent model, you change now just the number of electrons. Yeah, you go a bit more electrons, a bit less electrons. You can can guesstimate how many electrons you have to put to change the potential or the work function by a certain amount. You can guesstimate it, let's say, from an guesstimate of the of your interfacial capacitance, and so so you charge. So what you do is you charge your interface, or you charge your surface with these implicit solvent models with an electrolyte. You have no problem typically in the total energetics, because you get electrolyte countercharges in the solvent, and so the whole kind of DFT cell plus implicit solvent model gives you an overall charge neutrality. And so there's kind of no problem with let's say cell size dependencies or so that you would run into if you have effectively charged cells. And so kind of this is what you do. You sample like number of electrons and the number of adsorbats. And then you do what I kind of summarized here in this kind of Legendre transform. Then you subtract the energy cost of taking these electrons and particles from your reservoirs that you have to kind of define, or like as I put it there, or try to describe here in this talk. And then you minimize everything. And it turns out, and we described this in this paper that I in this paper in 2019, this JCP paper, it turns out, so this kind of abstract description with the minimization, it's kind of the same or very similar to what, so this is the paper here. It's kind of similar, or the identical in the idea to what Ross Meisel calls the generalized computational hydrogen electrode, which says that you take a system and you look at the work function, and you kind of then can only evaluate the energetics for systems where the work function corresponds identically to the applied potential, plus potentially some let's say shift. But there's a clear relation between, let's say, work function and the applied potential. Not sure if it's enough of a description. I think it can be helpful to read this paper, but I mean, there are also other people who have described this in a similar way, like Sundararaman and others. Or I mean, also Karen in Karen's group, of course.
So Nico, I just had a quick question myself. I was wondering, so in this paper that you showed where you do this band alignment stuff, I remember that you also computed an absolute SHE potential. And I'm wondering, so would you then say that whenever you do calculations with environ, that one has to use that value instead of the 4.44 just to keep the internal reference?
Yeah, so I think I took somewhere in the back here of, let me just see if I have this figure in. Oops. Nah, sorry. Yeah, maybe this is kind of, I think, what you referred to. So what we saw is, when we tried to find the kind of absolute alignment, and so what we did was basically we could kind of derive the absolute alignment for these all explicit calculations. And what we saw is that if we have these kind of mixed explicit implicit water or systems where we have at least one explicit water layer, it seemed like, okay, we get kind of this potential drop kind of consistent or kind of accurate in the simulations. But what we could still see is that when we look at the absolute alignment, that there was a kind of misalignment, let's say, on the absolute level, and a misalignment of something like minus 0.3 volt approximately. And this kind of also nicely related to a typically assumed potential drops at the water vacuum interface that we do not have in the simulations. So I do think you're correct. You're absolutely correct. I think what one would need to do is then to have the electrochemical potential of the ion shifted, or this kind of experimental reference rather that you use then to express the numerical value of the electrochemical potential of your ion, that you use here let's say experimental value that you shift by this kind of, with this number. Or you could also go the other way around and say, I have to kind of shift or change the absolute scale of my work functions or so that I derive from my DFT calculations by this kind of value if I want to be on the absolute potential scale.
Okay, great. Let me just go because we don't have a lot of time. Let me go to the next question, which is, can you please explain why, when treating number of electrons as a degree of freedom, the resulting Legendre transform of free energy is considered to be a minimization of G over this degree of freedom? Typically, doesn't such a Legendre transform correspond to a sum over the introduced degree of freedom? For example, the canonical free energy is a sum, not a minimization over microstates with different internal energies.
Okay, this is a very detailed question. So of course let's say of course, let's say there are several kind of problems. The question is, like, can you really say, if we look, what we typically do, if we look at a just a limited number of states or systems, if we look at a limited number of systems, could we, can we reasonably sample, this big enough configuration space so we can derive appropriately the the minimum in this Legendre transform? And you're totally correct. In principle, you should sum over the individual excess energies, and then and only this sum then would give you the estimate for the ground potential energy. But I think, let's say, the inaccuracy that you do by just taking the minimum is relatively small. In particular, it is if you go to, if you think of if you have a limited cell size, and then you would do the thermodynamic average, and you make the cell infinitely large, it turns out in this sum, which you would need to write down the partition function, for example, then it's essentially only the minimum structure that remains really relevant. So so I think it's it is not 100%, you're right, this description that I say you just take the minimum, it's not 100% correct, but you want to express the partition function and do these sums, and then correctly derive the free energy. Yeah.
Great. Okay. So next question is by Hendrik Heenan. Awesome talk. Follow up to infinite cell size limit. Isn't the work function change in that limit equal to 0? So would only the difference in capacitance weigh in?
Yeah. So this is an interesting point that I was also not expecting. And now I'm thinking, I should maybe have made this, well, we'll see if this paper gives a good enough answer to that. No, but it turns out that the work function difference, absolutely, the work function difference goes for two states, or let's say for the work function change by a single Azabad in the infinite cell side limit, absolutely it goes to 0, but the energy, that this energy expression that I put there, if you do this consistent limit, it doesn't go to 0, because there's two contributions. So, you can also maybe in a very maybe not totally valid relation, but you can in some sense understand it, I think. Looking at, for example, if you have just in mind this simple idea, you have a dipole that interacts with an electrostatic, with a field, right? And for example, the field, this field of, which would be the field between surface and your diffuse double layer in some way, this field would be not changed too much, right? Or this would be a constant field that you have there. And the dipole of your single Azabad is also always there, independent of your total cell size. And so this energy contribution, dipole interacting with the field, is always there, independent of the cell size. And this is not kind of, I think, totally the relation, or this is not, this is kind of just a bit more like the simple way to understand. Of course, there should be a difference if I take into account interactions of the kind of dipole with a field, or with this potential drop between surface and double layer. So at least, let's say it's kind of, it makes sense in this view. But in the math, it is kind of very kind of consistent. There's no problem to see that you have remaining terms. And yeah, I can only say this paper is hopefully soon out. So, or I can share it with you in private, of course.
Great. So the next question is a bit long. You can also probably read it. It's by Katharina, and it says, adding to question 1, you wrote J equals min of G underscore EXC, where you minimize towards all n. If I'm not mistaken, the n you should minimize for is actually the average n. Let's say you have a 1 cross 1 cell, then you would only have n equals 0 and n equals 1. This gets better, of course, as you increase the system size, but in the extreme case, you would have n equals 0 until you suddenly switch to n equals 1, and your grand canonical potential will not include any influence from n equals 1, which would actually shift the potential. Do you care? For example, will that influence change over potential?
So, yeah, I'm not 100% sure if I understand correctly, but so there's kind of one maybe core problem, or maybe you captured one core problem that I think that is absolutely kind of there. So the formulas I wrote down was kind of having in mind a fixed cells, having a kind of fixed cell size, and so this whole kind of math makes in some sense only makes only in, or is reasonable if you consider, say, fixed cell size and change number of particles in this fixed cell size. If you would really try to kind of write it down more abstractly, and so why I wrote it down like this is because you can kind of relate it directly to a computation with n particles in the system. Now, if you would want to describe it a bit more accurately, and what you say, like, for example, cell size independent, this kind of, let's say, minimization, yes, you would have to think of the appropriate normalization, and for all interface systems, that would be kind of either per surface area or per site. And in that sense, this minimization is rather to be done in this kind of per site or per area way. And so I think, if I'm not mistaken, your kind of let's say your comment that we get problems in the 1x1 cell with just one adsorbate or 0 adsorbate, that then kind of this whole thing makes no sense. I totally agree. You of course need to kind of look at system sizes that are big enough so you can kind of reasonably describe kind of halfway continuous coverage changes in this cell. And I think then you don't really get problems in the, let's say, minimization. But yes, you're limited always, but that's kind of a problem with all simulations, that you have always kind of integers in integer number of integer number of adsorbates, and then you can kind of not resolve in detail everything, or you cannot resolve the free energy at continuous kind of surface concentrations or something. So maybe, I hope this explains a bit.
Great. Okay. So I think we're almost out of time, but like the final question, maybe you can give a short answer. Can you just give well, I don't think you can give a detailed comparison, but maybe can you just talk a bit about your, the environ versus WASP solve?
Okay. Sadly, I can't be. I'm really not the best person, I must admit, to answer this question. I think that the people like the Karen Chan's group is here like the kind of right kind of people to address. I mean, they looked in detail. They use very often both codes or maybe even other codes, and they have, as I mentioned before, there's this paper by Gauthier from 2019. I think it's called practical considerations, something like this. Maybe he could write it in a chat if Gautier is listening. Sorry, is it the first name? No, Joseph is
Joe. Yeah, Joe.
Joe. Sorry, it's the first name is Joe. Sorry. Yeah. Well, the only thing, let's say, looking at this paper, for me, I have the feeling, and this is no criticism to anything. I have the feeling that maybe there are still kind of maybe some difficulties in treating really let's say these charged systems or the electrolyte. I'm not aware if something changed, let's say in terms of the periodic boundary corrections. So I mean, what they described effectively is that the electrostatic reference shifts for different cell sizes, and it shifts in a way that this also, at least that's how I read the paper, that it also influences the total energy. So you have a kind of total energy shift, and that kind of makes makes it, let's say, a bit more difficult to evaluate the kind of energy of a charged or consistently the energy of a charged, let's say, slab in this implicit model. So you need to introduce some kind of corrections afterwards. And I've always wondered, and maybe some other person can comment, I've always wondered if that is the case, if then the forces are potentially not 100% correct, if there's a discrepancy between let's say total energy and the Fermi level, or the electrostatic reference. But so this is all I can say. I was always a bit worried about this, but I couldn't say. Maybe it's fixed until now. Maybe it doesn't have to be fixed at all. Maybe it's a thing. Yeah. So
okay, I think, yeah, in view of time, we'll probably stop now. And then if there's any more questions, we can take it another time. But so thanks a lot, Nico, for giving the talk today. I think all of us enjoyed it a lot.
thanks.
And also,
yeah. So what you covered is very similar to a lot of things we've been discussing. So if you're ever around, we should do this live. Thank you so much.
Well, thank